In this unit, we are going to be looking at energy and disorder, which are both important concepts in chemistry. We will focus mostly on energy at the very beginning of this unit. Another name for the study of energy transfer is called thermodynamics. It is also known in chemistry as thermochemistry, where you look at the heat changes that accompany chemical reactions. And these chemical reactions can be exothermic or endothermic. And we've previously studied this, so I'm hoping that this information in the next few slides is a review. Now, energy cannot be created or destroyed. It can just be converted from one form to another. So this is called the first law of thermodynamics, and in that, the universe is constant. So when we look at something in chemistry, we're studying a system. So this could be a chemical reaction in my beaker. Everything around that beaker is the surroundings, and altogether it makes up the universe. So I know it seems a little bit far-fetched to look at a beaker and think about the universe, but that is how we describe surroundings, because where do your surroundings stop? So the chemical reaction that occurs in my beaker, it can either absorb heat, have heat flow into it, or it can have heat go out of it. When it has heat leaving the chemical reaction, recall this is called exothermic. So let's review and define what energy is, temperature, and heat, and how they relate to each other. First of all, energy is the ability to do work or to produce heat. And we focus on two types of energy in chemistry, kinetic energy and potential energy. And over here on the right, we have the classic physics example where we have a gravitational potential energy. So as the car goes up, then my potential energy increases. And then when it goes down, that gravitational potential energy is turned into kinetic energy or energy of motion. Now in chemistry, it's not necessarily the gravitational potential energy, but it is the energy that is stored in chemical bonds. That is the chemical potential energy. So when those bonds are broken and reformed, that energy is transferred into the form of heat. And when something heats up, those molecules move faster. So that's that kinetic energy, that energy of motion. So the potential energy in chemistry is the energy in the bonds, and then the kinetic energy, once those bonds are broken and reformed, then that energy is turned into those molecules moving faster. Let's define temperature. So temperature is the average kinetic energy of molecules in a substance. So I have two containers here in the yellow. I have one that has a temperature of 400 Kelvin, and one that has a temperature of 50 Kelvin. And the arrows describe how fast those molecules are going. So you can see with the arrows, some are going faster because the arrow is a little bit longer, and some are going slower because the arrow is a little bit shorter. So you see that you always have some going a little bit faster, some going a little bit slower, but the average would be measured as the temperature. So looking at the colder of the two, my 50 Kelvin, again, you see that we have some molecules that are moving a little bit fast and some that are moving really slow, again, based on the length of the arrows. This diagram over here on to the right also describes this. So the blue line, this is descriptive of a colder temperature. And you see that you have molecules that are moving slower, but you also have molecules that are moving faster. Now this red line right here, this is representing the activation energy. So above this certain energy, then those molecules can react in some sort of reaction. But you're always going to have some that are slow and some that are fast, and the average would be the temperature. I have another curve here in purple, and this is representing a warmer temperature, and you can see that it also has molecules that are going slow, but we have more molecules that are going faster. So you see that in this case, more molecules are able to achieve that activation energy, so more will be able to react. So temperature is a measure of the average kinetic energy. Not all molecules are going at the same speed. You're going to have some going slow, some are going fast, but the average is called the temperature. Chemical changes are always accompanied by a change in energy. So, and as I mentioned before, we're looking at a system or a chemical reaction, and we're looking at those surroundings to tell us what is going on in that chemical reaction. We actually can't measure the chemical reaction's temperature change directly. Instead, we're reliant on the surroundings around that chemical reaction. So I'm going to draw a little thermometer here representing that I can measure the temperature of my surroundings, and then that will give me a clue as to what is going on inside my system or my reaction. So in an exothermic reaction, I'm going to have heat that exits the reaction. In an endothermic reaction, that heat is actually absorbed into that reaction or the system. And so we will see that that heat decreases because it is going into the system. So our thermometer will register as the temperature is going down because that heat is being pulled into the reaction. So an exothermic reaction is when the energy exits the reaction and goes into the surroundings. And again, it feels hot. And we look at our surroundings to help determine what is going on inside that reaction or that system. An endothermic reaction, the energy enters the reaction from the surroundings and it feels cool. So a good example of this, if you touch a piece of metal, like the leg of a metal chair, you will have your hand register that it feels cool. And the reason it does that is because it is taking the heat from your hand and pulling it into the metal. Now, if you had a piece of metal that's been sitting out into the sun on a summer day, when you go to touch that piece of metal, then the opposite occurs. We say, oh, it feels hot. And that's because when we touch it, the heat goes from the metal into our hand. And so our brain interprets that as it feels warm because the heat is leaving that metal and going into our hand. And in fact, in a really, really hot summer day, you could get burned if you hold on to that piece of metal long enough and if it's a hot enough summer day. You should be familiar with these potential energy diagrams. You should be able to draw them. You should be able to identify where the reactants are and where the products are on each one of these. And you should be able to look at the graph and determine if it's an exothermic or an endothermic reaction. In an exothermic reaction, the products have less energy than the reactants. As a result, the heat will leave that reaction. Now, another name for heat or a symbol for heat is delta H. And this is also known as enthalpy. Now, notice in the word enthalpy, there's an H right here in the middle. So hopefully that will help remind you that enthalpy has the symbol of a delta H. So we've talked about exothermic reactions and how heat leaves and that it feels hot because the surroundings get warmer. But let's look on the diagram for that delta H. So that delta H is the difference between products and reactants. So if I take the amount of products I have and I subtract the amount of reactants, that difference is my delta H. And for an exothermic reaction, it's going to be a negative number. And that's because the products are going to be lower energy than the reactants. And if you take a low number and subtract a higher number, you're going to get a negative number. So delta H is negative for exothermic reactions. In an exothermic reaction, the heat is always a product. So for example, if I had this reaction, A going to B. So A is my reactant, B is my product. I would have heat be on the product side because the heat is produced and it will leave the reaction. All right, let's go ahead and look at an endothermic reaction. So in an endothermic reaction, the reactants are at a lower energy than the products. So when I calculate my delta H, and again, I do products minus reactants, because I have a large number and I'm subtracting a smaller number, I'm always going to get a positive number. So my delta H is positive. And this is because heat is being added to my reaction. So if I were to write a sample reaction for an endothermic reaction, so let's say A going to B. So A is my reactant, B is my product. I would put heat on the reactant side because I'm adding heat to my reaction. So it is a reactant. So you can look at your delta H as positive or negative, and you can look at your heat being on the product side or the reactant side. So again, you need to be able to sketch a diagram like this and identify the parts on the diagram. The reactants, the products, and in previous lesson, we've talked about activation energy. So the activation energy is the energy required to go to form this activated complex. And then it will slide down to form the products. And it does that in both the endothermic and exothermic reactions. All right, so heat is this delta H or enthalpy. In the laboratory, we also call it a Q. So I know that's a little bit confusing, but we've actually seen this before. We have talked about the formula Q equals mc delta T. So this Q, again, is another way to describe heat. It's just done in the laboratory setting, and so they give it the letter Q. So sorry, that's so confusing. But a lot of synonyms here with heat. Heat, this is the flow of energy due to a temperature difference. In this little diagram right here, I have a very cold, and I'm sorry the color's red. I have a very cold glass of water, and I stick it into a larger glass of water that has warm water. Well, what's going to happen? You're going to have an overall direction of molecules colliding with each other, and you will have those molecules transfer their heat into the container with the cold water and then into those molecules that are moving slower, that are cold. So the overall direction, again, is from warm to cool. And eventually, everything will be the same temperature. But with heat, it will always flow from warm to cool. So cold can't flow. Cold is just the absence of heat. So again, the heat always goes from high temperature to low temperature. There are different units for measuring heat. One way in chemistry is to use calories, and this calorie is really, really small as compared to the calorie that we eat. So if you look on the back of your animal crackers and it tells how many calories are there, those are calories with a capital C. So there's actually 1,000 of these little tiny chemistry calories that are in that one food calorie. The definition of calorie is the heat required to raise the temperature of 1 gram of water by 1 degree Celsius. Specific heat is very similar to this. This is the heat required to raise the temperature of 1 gram of any substance by 1 degree Celsius. And you'll also see the unit for heat and energy, and that is joule. And this is a even smaller unit of energy. And we've dealt with joules before when we calculated how many joules it takes for an electron to absorb a photon and jump to a higher energy level and then to drop back down to its ground state. So these joules, again, are really, really small. And I put the conversion right there. You're not going to have any problems on it, but I just think it's interesting. Calories are small, but joules are even smaller. All right, what is a conductor and what is an insulator? So a conductor, it transfers heat energy very easily. And metals are good conductors. So looking at the periodic table, most of the periodic table are metals. So the whole left-hand side and the middle, those are all metals. Insulators, those are non-metals. So all your non-metals are insulators. And they do not transfer that heat energy as easy. So why is the blacksmith, why does she need to wear gloves? I can look at that piece of metal and it's only hot at the end. Why is she wearing a glove clear at the other end? Well, and the answer to that is metal's a very good conductor. So even though I can tell visually that is very, very warm where that orange is, so this is very, very hot, it will still get hot here because those molecules will vibrate and bump into each other and they will move along this piece of metal and it will get quite warm. And so she's wearing some leather gloves that give her some insulation that don't transfer the heat as easily. They're probably pretty thick, and so she'll be able to hold on to this hot piece of metal for a long time as she works with it.